What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
This is the story of the one. As a maintenance engineer, he hears things differently. To the untrained ear, everything on his shop floor might sound fine, but he can hear gears grinding or a belt slipping. So he steps in to fix the problem at hand before it gets out of hand. And he knows Grainger's got the right product he needs to get the job done, which is music to his ears. Call, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
A numerical base is a system of representing numbers using a sequence of symbols. However, like any mathematical concept, it can be extended and reimagined in many different forms. A term used occasionally in mathematics is the term exotic, which just means different than usual in an odd or quirky way. In this episode, we are covering exotic bases. We will start with something very familiar, that is to say, decimal points, as a continuation of our previous episode, and then progress to the more odd, such as non-integer and complex bases. So how can the base systems we covered last time be extended to represent fractional numbers? How can fractional numbers be used as a base for integers? And what is pi plus e times I in base I plus 1? All of this and more on this episode of Breaking Math. Episode 51? Episode -201. This is Sophia, and with me I have Meryl, who's a graduate student at UNM. Meryl, thank you for being on the program.
Thank you.
All right, so before we get into the subject, I got a few plugs. Patreon, we're on patreon.com/breakingmath if you want to support the show monthly. $1 or more for outlines and ad-free episodes. We also have a poster store on Facebook at facebook.com/breakingmathpodcast. The poster tier on Patreon will give you a podcast. Will give you a poster for like, I think it's like $35. But the poster store on Facebook, it's considerably less. It's $15.15 for a tensor poster, plus $4.50 shipping and handling, which is $19.65 anywhere within the United States. This tensor poster has the mathematics behind tensors and a little introduction to general relativity on it. What else? Oh yeah, on Facebook you can find updates about the show. We're also on Twitter at Breaking Math Pod, and our website is breakingmathpodcast.app. That is breakingmathpodcast.app. Meryl, welcome to the show.
It's good to be here, Sophia.
We sound like a news people.
I know, right?
So, bases. Any thoughts about bases?
Well, as a computer engineering student no, I'm not a computer engineering student anymore because I got my bachelor's in that and went on to go for a PhD in pure math. I feel like I at least know something about bases, having to deal with them all throughout a computer engineering degree.
And of course, the bases that you deal with mostly is
2
yeah,
or 16
or 8 sometimes.
Maybe 8. Usually 2 or 16.
Yeah,
if you're lucky, 10.
So last time we talked about what a base is. We talked about base 5 and how, like for example, 2, 4 in base 5 is equal to 14. If you want to know more about that, just go to episode 50, which is our previous episode. But right now we're going to be talking about how to represent fractions in bases, and then it's actually only a short leap there to using bases that aren't even integers. They're not whole numbers, and they're not and even bases that are complex. All right, so without further ado, here's the episode. All right, we're going to do a review of bases. Base 10. What do we use for base 10? The Hindu-Arabic number system, which is what?
It's, 1 through 9, or I guess 0 through 9, and just, you have your tens, your ones place, your tens place, your hundreds place, and so on.
Yeah, and a example of a system that isn't base 10 is Telephol, which is a language of the Telephol people from New Guinea, which is base 27. They have different numbers from the left pinky to the left thumb, the wrist, lower arm, and so forth on the left and right side of their body, meaning that they just have to remember which part of their body is to remember the number less than 27. And a large number in Telephol is 14 times 27, which would be 378.
I can just imagine with like that particular base 27 system just having to do an entire dance to count, and I kind of want to see that now.
Oh, yeah, I mean, you could try it right now, listeners, and just like use your right index finger as a cursor and touch your left pinky, left ring finger, left middle finger, left index, thumb, wrist, lower arm, elbow, upper arm, shoulder, side of the neck, ear, left eye, nose, and then just all the way on the other side, you use your right index finger to point to that. So really, for any number less than 378 times 2, which is 556, you can use 756. You can use you can just remember 2 parts of your upper body. But then also you can remember 576 now. But non-10 bases. So if we're in base 5, our positions go 1, 5, 25, 125. If we're in base 60, how do they go?
So they go 160, whatever 60 squared is, I guess 3,600.
Etc.
Yeah.
Keep multiplying by 60. Base 10 has how many digits?
10.
Base 5 has
5.
And base 60 has
60.
And there we've reviewed bases. All right, so the first thing we're going to talk about is the radix point, known in decimal notation as the decimal point. And it's used, of course, to represent non-integer numbers.
Okay, like I was just, interjecting a minute ago, how we have our ones, tens, hundreds, places, or so on for base 10, or our...
Going left, of course, right?
Right. So, but what if we're going to the right of the decimal point? Then we have... our tenths places, our hundredths places. Notice the emphasis on the TH because we're going with, fractions this time. So it's like, say I were in binary, base 2, then we would have our 1/2 place, our 1/4 place, 1/8, 16th, 34th, 64th, and so on.
So what would 0.11 be in base 2? Would you like to go through that?
So let's say that we had the number 0.11 in base 2. So we have past the radix point, we have a 1. So that first one is in the 1/2 place.
And why is it in the 1/2 place in binary?
So we have that pretty much any base has, especially integer bases, has a ones place. So... that is because it's whatever your radix number is.
Yeah, it's like home base kind of for the number.
Yeah, so it's that to the power of 0, and that's just 1. And then past the radix point, we start going to the negative ones place, like the negative first power, negative second power, and so on. So
yeah, because just a quick review, 3 to the negative 2, for example, is 1 divided by 3 to the power of 2, or 3 squared, which is 1/9.
Exactly. And so in this case, if we're talking about the number 0.11 in binary, then we have 1, the first place past the radix point is 1/2, and then we have the next part, which is the 1/4 place. So what we can say is that this is the same thing as 3/4 or 0.75 as we would write it in decimal.
Because it's 1/2 plus 1/4, right? And there's 1/2 times 1 plus 1/4 times 1, right?
Exactly.
And so 0.101 in the same vein would be 1/2 plus 0 times 1/4, which is just 0, plus 1/8, which is 5/8. So, so the development of these numerals was actually surprisingly late. We talked about how Hindu-Arabic numerals had been around in the early first millennium. But but it wasn't until the 10th century AD by Abu Hassan al-Uqlidisi, a mathematician and kind of polymath, who wrote a book called Arithmetics of al-Uqlidisi, original title, Kitab al-Fusul fi al-Hisab al-Hindi. In every translation I've found, it says it's called the Arithmetics of al-Uqlidisi, but I noticed that there's this al-Hindi in there, and I haven't had time to research the original Arabic, but something tells me that there's a reference to Hindu Arabic numerals inherent to the title that hasn't been translated. And I think it's just weird how long it took. And I think part of the reason why is commerce isn't always, okay, like you go to the store, you don't buy 10 eggs, you buy a dozen eggs, right?
Right.
So, I mean, I don't know. Why do you think it took so long from the time that Arabic numerals were introduced to talk about decimal points?
Instead of, breaking numbers into smaller numbers, you just use smaller units of measurement. And it's like, that 12 inches make a feet. You're not as likely to think about how 3 inches is a quarter of a foot.
Oh, yeah, and which is 0.25, which is 2 whole decimal points. So it gets very abstract, I suppose. Even the Sumerians, in my understanding, when they used fractions, they would just use fractions instead of using decimal points, even in base 60. Or if they did use it, they would, it was not with a radix point. It was just understood to be divided by something else. So it is hard to kind of pin down the beginning of this, I suppose. So then you have Manuel ben Jacob von Thiel, who lived from 1300 to 1377. He was a pioneer of exponential calculus. He used decimal fractions, and he was a French Jewish mathematician and astronomer. And he wrote this book called Six Wings. It was a book of astronomical tables, eclipses, and stuff that was used for 300 years by sailors and explorers, until the 1600s. But he used, and he was the one who used the fractions for the first time. In 1585, Simon Stevin, who lived from 1548 to 1620, wrote a book called De Tiende. I think it's De Tiende. And I apologize if I've been butchering things. All these names are things I'm fairly unfamiliar with. But he lived this book was written in 1585, and it means of tenths. In this system, to write 120.21, you'd write 120. Then you write a circle around a 0, and then a 2, and then a circle around a 1, and then a 1. Meryl, isn't this great? Isn't this a great system?
It's hideous. And I just want to say, so you have 120, and then you have... So what is, the circle 0? Is that saying, the power 0 is to the left? Is the circle 1 saying that the power to the -1 is to the left of that? It's just... considering that you read from left to right, it seems pretty counterintuitive.
Oh, yeah, and it just seems counterintuitive, too, because, 3.1415 would be 3 circled 0, 1 circled 2, 4 circled 3, 1 circled 4, 5, and why? Why? But so it didn't take long for people to write a bar over the units digit. So 120.21 would be 1, 2, 0 with a line over it, 2, 1. And then superscript, which is actually still using prices, with the 599 with the 99 up and to the right of the 5. And then, of course, decimals came into play at some point. It was in the next century.
Except for in Europe where they use a comma.
Yeah, so certain places in Europe, I believe. All right, so we talked a little bit already about non-10 bases for decimal points, or I suppose radix points, but just something kind of interesting. We're just going to give you a couple of facts about that. If you have a calculator right now, if you type in 1, 2, 3, 4, 5 divided by 99999. Of course, you don't have a calculator, you have a phone, but type it into the calculator app and you'll get 0.12345, 12345, and it'll have 1, 2, 3, 4, 5 over and over ad infinitum. And if you notice, that's because I had 1, 2, 3, 4, 5 numerals over 99999, which is 5 numerals. And surprisingly, this works in other bases. So, for example, 3, 4 divided by 4, 4 in base 5 would be 343434. And one interesting thing about binary is that pi in base binary, actually base 16, which is closely related to binary, you can write out the decimals of pi, and there's actually a definite expression for each decimal. It's like a summation or something, but there's a formula for each decimal. As far as I know, there's no known ways of doing that in other bases. I don't know if it's been proved that it can't be done though. All right, so how would we do non-integer bases? So as I was doing this podcast, I was just thinking about it. In the last episode, like let's say we wanted to convert to base 2, we did it from right to left, from the units digit to the like 1, 2, 4, 8, 16, etc. And what you do is you divide by 2. So like if you 17 in base 2, 17 divided by 2 is 8 remainder 1. So the last digit is 1. 8 divided by 2 is 4 remainder 0. So you take the remainder, which is 0, which is the second digit from the right, and so on. So then you get 11101, I believe, or something like that. Oh yeah, no, it's just 10001.
Yeah, just take a 16, tack a 1 at the end, and you got it.
Yeah, but so there's another way that we could have done that. Let's say we wanted to convert 17 to base 3 using this. The largest power of 3 that fits into 17 is what?
That should be 9.
Yeah, 9. And that goes into 17 one time, right?
Right.
And 17 minus 9 is 8. And then, okay, so the power over from 9 is a 3. And 3 goes into 8 twice. So the number so far is 1, 2. And then the last digit is just 2, because 1 goes into 2 twice.
Right, so the last digit kind of acts as a remainder in this case.
Yeah, which is kind of weird. I suppose that makes sense. Yeah, every single time it's going to be a remainder. But basically, there's nothing in this algorithm that stops us from doing it with non-integers. And so basically, if we're doing base pi, we just have to keep multiplying pi by itself until we're less than a number, and then divide, and so on. And we'll leave this as an exercise to the reader. We might talk about this in a problem episode. But just kind of for fun, 1/2 in base pi is 0.1121120212020. And in fact, this number I'm pretty sure would be transcendental. Don't quote me on that, because God knows that not every postulate is correct.
So I actually do have a question about this one. So I noticed that it's base pi, but your digits are all 0, 1, 2, 3. So...
Yeah, and I was just using the convention in this case that all the digits would still be decimal. I mean, would still be integers, and all integers less than pi.
Okay, I can see that then.
Yeah, and so E in base pi would be 2.20212010002. But what's cool is that 1 divided by pi in base pi is just 0.1, and 1 divided by pi squared in base pi is 0.01. But 1 divided by pi squared times 3 is 0.10220122202, and it just goes on forever. So it's just weird to add two things that have finite representation together and get something that has infinite representation.
And something I actually kind of noticed about that is, so you're just, because remember, pi is transcendental over the rationals. What we're doing here is that we're just taking, say, taking pi, plugging it into a polynomial, and then you're getting something based on that. So it almost makes sense that what you get in base pi would be some sort of, say, repeating decimal.
Yeah, I didn't even think about it that way, but yeah, that totally makes sense. And yeah, that kind of covers that aspect. However, there's another way we could write, we could do fractional bases. Okay, so this method of fractional bases only applies to rational numbers. And do you want to talk about what rational numbers are super quick?
So if you study math, the definition of the rationals that we get is that we have A divided by B. A and B are just some integers, and B is not 0.
Yeah, so 3/4, 1 over 307, 307 divided by 308, but yeah, etc. So in base 10, you ever play Mancala?
Yeah.
So Mancala is this game where you have a bunch of different wells with little stones in them. And this is nothing like Mancala. The rules of Mancala don't apply here, but I just wanted to just imagine in front of you that you have a board filled with a few different wells that you could place stones in, small colored stones. Now let's say that we're counting in base 10. We put one stone in the furthest right well. We add another stone. Now we have 2 in the furthest right well. We continue until we have 9. But then when we have 10, we take out all the 10 stones from the well that has 10 stones. And in doing that, add 1 stone to the well right next to it. So now we have a well with 1 stone next to a well with no stones in it, which is kind of like the number 10, 1, 0. Are you with me so far?
Yeah, actually, I've never even heard this explanation before, so I need to remember to buy a Mancala set if I ever end up teaching digital logic.
Yeah, and also then people can play Mancala as a treat, because Mancala is fun. And then for all you who don't know, Mancala is a really old game from, I think, Africa, where you just but I'm pretty sure like a ton of cultures have their own version of it, where you move stones around and you have to collect as many stones as you can, and it's a whole thing. All right, let's say though that we're in base 3, right? When we'd have start with 1 stone on the right, 2 stones on the right. But when we have 3 stones on the right, we replace those 3 stones with 1 stone next to it, right? So we have 1, 0, meaning 3 in base 3. Then 1, 1, 1, 2, 1, 3, but 1, 3 doesn't exist in base 3. So you take the 3 stones and you replace it 1, 2 with stones next to it. So you have 2 stones next to no stones, or 2, 0 in base 3, which is 6 in our system. So then you have 2, 0, 2, 1, 2, 2. And then when you get to 2, 3, you take away the 3 stones and you add 1 stone to the well next to it, which now has 3 stones. So you have 3, 0. However, 3 can't exist in base 3. So you take away those 3 stones and you add a 1 to the stone, to the well to its left. So you have 1, 0, 0 in base 3.
And that's just 9.
Yep.
As we know it.
So let's say, though, that instead of taking out 3 stones and adding 1 to the well next to it, or taking out 10 stones and adding it to the well next to it, or taking out 64 stones and adding it to the well next to it, this is a big Mancala set. Suppose we took out 3 stones and added 2 to the one next to it. In this episode of the podcast, we talk a little bit about infinite bases, and that's why we're recommending the brand new Infinity course from the folks over at Brilliant. It's a course all about the math of infinity. Explore exotic concepts such as infinite area and more on this course. So what is Brilliant? Brilliant is a website that teaches various concepts using text, videos, diagrams, and interactive demonstrations. With an approach emphasizing problem solving and active learning in over 60 courses in math, science, and computer science, Brilliant is a great place to start learning a ton of concepts that you, as a listener of Breaking Math, may be interested in. So if you're interested, you can go to brilliant.org/breakingmath. The first 200 Breaking Math listeners can get 20% off the annual subscription. Now, back to the episode. So let's say we're doing 3 stones to 2 stones, right? Let's start with the Mancala set. If I add a stone to the right part of your Mancala set, you have 1, right? No, right? Add another stone, you have
2.
Add another stone.
So you have 3, but you take those out and then you add 2 to the next one over.
Yeah, the one to the left. So now we have 2 stones and no stones, right?
So we got 2, 0.
Yeah, and then I add a stone to the right, and now we have...
So 2, 1.
We add another stone, and we
2,
have...
2.
And then...
So we'd have 2, 3, but we'd have to take those out and then add them over, but we're adding 2 to the next one over, so we got 4, 0.
Yeah, so we have 4 stones in the second slot to the right, from the right, and then in the rightmost spot we have no stones. However, 4 is greater than or equal to 3, right? So because we're doing 3 to 2, we have at least 3 stones to grab, right?
Right.
So what happens when we take 3 stones from 4 stones?
So if you take 3 from 4, then what I'm guessing is, because we know that 4 in this base would be represented as 2 and then 1, what I'm guessing is that we move, so we take all but 1 stone out of that second place, and then we have 2, 1, 0.
And that is actually correct. Yep. Actually, it's correct. No, but yeah, it's correct. So 210 is the next number. And here's what's interesting is that 210 in base 3 halves would be 2 times 1/2 times 1/2, which is 2 times 2.25 or 4.5, plus 1 times 3 halves, which is 1.5, plus 0, which is 4.5 plus 1.5, which is 6. So it actually works as base 3 halves.
I think you just broke my brain.
Oh, I know, this broke my brain when I found it too. And for an explanation of why. Oh, and by the way, if you hear sounds, it's because we moved into a new place and things are still moving around, but we'll be able to provide more regular episodes for you now. What you hear in the background is a dog we known as Math Pig. But yeah, for the reason why we might do that on a problem episode. If not, it's left as always as an exercise to who?
The reader.
Yeah.
Or I guess the listener in this case.
So yeah, that is how to, and you could do that with any fraction greater than 1. It's distinct from the other notation because in base 3 halves in the other notation, we only have digits 0 and 1. However, in this one, we have digits 0, 1, and 2, right? And the difference is the numerator. And actually, there's a theorem that states that basically any fractional number can be represented in an infinite number of ways with digits if you don't limit the digits in the bases. All right, so infinite bases, super quick. Everything is super quick. But no, infinite bases, the way it works is just by never carrying, right? So you have 1 on you just keep counting. If you just keep adding 1 to something, you only have 1 digit ever. If you multiply them by like 1 0 in this base already, then you could get up to that. And the only reason we mention this is because Pascal's triangle. Do you want to explain Pascal's triangle really quick?
So, about the binomial theorem, I'm teeming with a lot of news. No, maybe edit that.
I am very well acquainted with matters mathematical. I understand equations both the simple and quadratical. About binomial theorems, I'm teeming with a lot of news. Lot of news.
Papa?
With many cheerful facts about the square of the hypotenuse.
With many triple facts about the square of the hypotenuse. Many triple facts about the square of the hypotenuse.
How bad it was. Alright, so about the binomial theorem, I'm teeming with a lot of news. Pretty much, you start with 1, and then the next row is 1, 1.
So on the piece of paper, you could write the number 1. And then if you draw 2 diagonal lines from the 1 down to the sides, you just write 1s on each of those. But then what do you write beneath each of those 2 1s?
Right, so it's like you have 1, and then you have 1, 1. And then, so you have, on the left side, you'll have 1. And then in the middle, you'll have, so that's between 2 digits. You add those, they're just 1s. So 1, 2, 1. And now...
Yeah, because 2 is 1 plus 1, which is the above it. So then you have 1, 2, 1. And the next row would be 1. And then 1 plus 2 is...
3.
3.
Then
3.
2 plus 1...
Yeah,
is
3.
3, and then you end with 1.
Yeah, so 1 3 3 1. Next is 1 4 6 4 1, 1 5 10 10 5 1, etc. All right, so how is the Pascal's triangle related to the binomial theorem?
So we all know that if we have something that's just a plus b, we're adding 2 things together. So that's just to the first power. So that's just the 1 1 row of the triangle. But let's say we're doing a plus b all in parentheses squared, and then we know that's a squared, so that's the 1 for the coefficient,
because it's 1 times a squared, yeah,
right, plus 2ab
2 times ab
plus b squared.
Yeah, and then the next one, the numbers without the r would be a. So let's say we're doing a plus b cubed. The a and b combinations, I can't remember what those the variable combinations we're going to do. We're going to be a cubed, then a squared b, then an ab squared, then b cubed. You notice that the power of a goes down each time and the power of b goes up each time. And then the coefficients are,
so we'd have 1 3 3 1,
and that's the 4th row down, 3rd row down, 4th row total of the Pascal's triangle.
Right.
And
so it would be, a cubed plus, and then we'd have 3 a squared b plus 3 a b squared plus b cubed.
Yeah, exactly, and so on. And why do we mention all of this? We mention this because 11 or 1 1 in an infinite base to the nth power is the n plus 1st row of Pascal's triangle. So, for example, yeah, 1 1 is basically do this, multiply things together, like multiply 11 by 11 multiple time and keep multiplying by 11, but just never carry your digits. Never carry over from one digit to the other, and you'll see that this works.
Yeah, so I just want to make sure I actually understand that. So we know that But wait, doesn't that work just for base 10? Like 11 squared is 121, 11 cubed is 1331?
Yeah, it actually devolves at a certain point because it's 1,121, 1,331, 1,4641, or 14,641. But then when you go again, it starts carrying over. So you have 161,051, and that's not good eats.
I see where you're going now.
Yeah, so that's pretty much why that works, because it's just adding the number to the next number.
Okay, so what I'm curious about, though, is what decides what digits go in what place in an infinite power?
Everything just goes in the last digit if you're doing integers. All the numbers are infinite if they have any more than one digit, or infinitesimal if they're to the right. Meryl has questions.
I mean, I'm mostly just trying to wrap my head around this.
And it doesn't make much sense outside of just like, I mean, infinite base is just another way of saying don't ever carry. But if you start off with a few digits, like 11 in base infinite would be like infinity plus 1, which is kind of silly.
Yeah, I'm just trying to figure out if you'd never carry, how do you get more digits?
Oh, by multiplying. Because when you multiply, the
I'm finally starting to get it.
yeah, because you get the last digit, which is just the last two, and then you go to the right, and then you just keep going. And then if you multiply two numbers that have a certain amount of digits, the product has the number of digits combined at least, or in base infinity, of course, at most.
Okay, this is starting to click. This is what I get for being a computer engineer, and the only bases are 2, 10, and 16. Maybe 8.
Basic bases. Yeah, because I mean, this is of course incredibly important to the human race, all this research about complex bases. But no. Okay, let's see. Complex bases, finally. But now we're going to finally talk about the very strange concept of complex bases. And there's already complex bases out there, which basically the base is a complex number. Like, and a complex number is square root of square root of 1 times some number plus some other number. So like -1 plus or minus I. Because I is the square root of negative. That was math pig. Because I is the square root of -1. So now let's talk about quater imaginary base for just a second. It's used sometimes in dragon fractals and things like that. It uses digits 0 and 1. But moving on. Breaking Math has an exclusive version of complex bases that I haven't found anywhere online. It uses Gaussian integers as digits. So basically Gaussian integers are like 3 plus 2i or 2 plus 5i, but not like 2.3 plus 3.8i. Because of the decimals.
So it's the same definition as a complex number, a plus bi. It's just that a and b are integers.
Exactly. And the magnitude of the digits is not more than the magnitude of the base in this system. That's how it works. And the digits, basically it's the same algorithm that we used, the first non-integer algorithm. And just a quick, we'll talk about this on a problem episode if we have time, or maybe we'll write a paper about it. We'll let you know. Pi plus ei, as promised in the intro, in base I plus 1 is -i 0 0 1 point -1 -i 0 -1 -1 -i, etc. It goes on forever. You can represent any complex number with no sign and no I. It aside from the stuff that's in the digits themselves.
Right. So I guess I'll start it. So I had a question here, and I was noticing like in like certain places we have things like we have both I and -I, and I'm a little curious how that works.
Oh, no, those are just written too closely together.
Oh, yes, but so there's still I's and negatives I's.
Oh, yeah, because I, -I, 1, and -1 are all less than or equal to the magnitude of 1 plus square root of 1 minus square root of.
Okay, so it's all about magnitude and not just,
Yeah, and actually this relates to the Gauss circle problem, which relates how many lattice points are in the circle of a given size and how quickly it grows over time, which is not as simple of a problem as you might think. It's kind of a fun one, though.
And I'm also curious, do you know that if in this base, does every number in the every Gaussian integer, let's say, or I guess complex number, since we have a radix point, does each one of those still have a unique representation in the space?
Yeah, constrained like this, it absolutely does. They have unique representations. I did a quick back of the envelope proof, but more research is needed. Bases can be simple or complicated. Your life using base 10 has shown that they could be simple. We have just shown that they could be complicated. We had no reason for doing so, other than it's kind of cool. And sometimes that's all you need to do math. I'm Sophia, and this has been Breaking Math. With me, I had on Meryl. Meryl, thanks for joining me.
Hi, I'm Meryl Flaherty. I am a PhD student at UNM in pure mathematics.
And again, sorry for all the extra noise. It's because moving studios, everything's half moved, all that. The old place was really hard to record at. Suffice it to say, it was a pretty terrible apartment, but now everything is much better, and we hope to produce regular content again. The Patreon is patreon.com/breakingmath. Facebook is facebook.com/breakingmathpodcast. You can also see us on Twitter at breakingmathpod, and of course check out the sister of the show to this, Touring Rabbit Holes, starring Gabriel and Alex. Meryl, anything you want to plug?
Is there? I don't think there is.
All right. Math Pig has something that he wants to say.
For the ones who know safety isn't a catchphrase, it's a culture. And the ones who help make sure everyone makes it home safe. For the safety-minded who watch everyone's backs, Grainger offers supplies and solutions for every industry, as well as safety assessments and training to keep your facilities safe and your people safer. Call, click Grainger.com, or just stop by. Grainger, for the ones who get it done.